So hello everyone. I will start my topic today. So my topic today is WebKit everywhere, secure or not. And let me introduce the agenda. So firstly, I will describe the WebKit background. And also because recently a lot of security features and exploitation mitigation has been introduced, I will also talk about them. And the most important thing is I will release and disclose details of CVE 2004-1303, which King team present in Pontoon 2014. And also I will give some suggestions to WebKit. So the agenda is a bit longer, so I may talk longer than expected. Sorry for that, and I hope that it will not make you hungry. Yeah, so firstly, my self-introduction. So I'm a chief security researcher at King Team, and of course, I'm a black hat. And also, I specialized in browser exploitation, including Chrome, Safari, IE, Flash, etc. And also, I'm the winner of two Pontoon events. One is Mobile Pontoon 2013, and another is Pontoon 2014, ponying the Mac OS Safari category. So first, let me introduce WebKit. So because everyone knows WebKit a lot, it is the most popular web rendering engines in the world. So the only thing that we need to take care of is there are two code versions of WebKit. One is the trunk and another is branch. So the trunk usually introduces new features and it is updated very frequently. Maybe it will introduce a lot of new features in one single day. And for the branch, it is used by Safari product, which is released version, so it will be updated less frequently. And also, WebKit will work along with the JS engine, either V8 or JSC, which allows hackers to do some bad things, which is good for the exploiter. So currently, WebKit is used everywhere. We have browsers or some PC application or mobile applications, and usually a single bug. If it's in extreme situation, it may destroy all of them. And historical issues, we have some DOS issues which happened frequently. So the most famous incident happened last year is Arab character issues, which will make the iOS 6 applications crash immediately. And it also impacts some versions of macOS. And also we have the UXSS, Universal XSS vulnerabilities, which may leak the information to the hacker. And also the most severe vulnerability is, of course, the remote code execution. So it has logical issues, also the memory corruption issues. But logical issues, because with more and more strict code review mechanism, it almost extinct. But for the memory corruption issue, it will keep existing for a long time. And it is also possible to use it to pwn the whole device. So it is my major focus in this presentation. And memory corruption issues has many categories, such as heap overflow, type confusion, and UAF. But you will find that in the public, you can only find very rare real cases of WebKit exploitation. Some of them are JSC exploitation, but WebKit exploitation is not quite many. So the typical example is Neil's Pontoon 2013, which he used a type confusion vulnerability to pwn the latest Chrome browser, and also the Pinkie Pie's Chrome exploit in Linux 64-bit, which is very exciting. And the reason why recently there is not too many public exploits for WebKit. So because WebKit introduced some new features and exploitation mitigations, and also some other vendors like Google joined the program to help to improve the security of the WebKit, which will make WebKit exploitation really hard. So the first concept is heap arena, which is a similar concept with IE, isolate heap. So it will put all those frequently updated objects. The typical example is render object. So render object will be updated when the layout tree is changed. So it is updated very frequently. And in our cases, based on our fuzzing test, it contributes for more than 90% WebKit UAFs. So you may need to find a general way to exploit the heap arena. Otherwise, those UAF will be wasted. So the render arena will be created for each document when the document is created. And internally, it maintained a single linked list with a nest pointer to some other blocks to store those free lists. So it also uses last in, first out mechanism when allocating the render object. So from the exploiter's view, you just need to overwrite the next pointer to a controlled buffer and then try to allocate the render object with the same size so that the user controlled buffer will be returned to the user, and you can leak the vtable and achieve RCE. That's for the history. But now render arena has some enhancement, which is the next pointer is XORed by a random value, which almost killed all the exploits in render arena. And also, but this only applies to the WebKit branch. In the trunk, there is no render arena concept, so you can still exploit some third-party web view or some applications without render arena being implemented. And the second one is the GC mechanism. Unlike IE and Firefox, you can just call the GC function by some interface. There is no such interface in GC, although some security researchers like Charlie Miller found some way to use number heap previously to trigger GC. Nowadays, the function collect all garbage can be never triggered by any function. And on the mobile device, it may be easier because resource is not enough sometimes. And for the PC, the Mac, on the Mac platform, it is hard. Even you use up all the memory, it will not trigger the GC. So for debugging purpose, it is very easy. You can just compile the code to modify and add some code to explicitly trigger the GC, which is possible, but it only applies to for the debugging purpose. In the real world, it is not feasible. And recently, Ian Beer, in his Project Zero blog, he published a way to do the heap layouting without GC. He reserved a memory and then do some thing he wants to do, and he can trigger. He can free that buffer and then put the reliable object to that hole, which is very good and can be used to resolve most of the heap feng shui issues. However, that's not enough in some cases, and sometimes it will not meet the needs for the exploiters. So today I will introduce a new technology called JS Control Free, which I will introduce later. And of course, ASLR is not a very advanced technology, but on different platform, the ASLR random level is not the same. For example, on iOS, the ASLR is weak because of the DYLD shared cache. So, which means all the modules share a same base. However, on the macOS, the ASLR is much stronger. Because each module has two independent base, one for the data and one for the text, which indicates that if you leak the vtable, it doesn't mean that you defeat ASLR, because you have to leak another base, which is the text base, so that you can perform a ROP. And also, DEP is not a very advanced technology. It is implemented by almost all the platforms. And the last one is sandbox. So sandbox is regarded as the last layer of protection, which limited the scope of the exploiter to do some bad things. And it has many sandbox types. One is typical example is the Apple sandbox, the Android sandbox, as well as some third-party sandbox. The typical example is the Chrome sandbox. So also you have nowadays more and more apps are native 64-bit. So the typical example is the macOS and the latest iPhone and the iPad platform. And in the future, I believe the Android platform will use the native 64 app, which indicates that heap spraying is not very effective. And you have to work around this issue. Maybe you can try to avoid heap spraying. So because the exploitation on web browsers, especially WebKit browsers, is very difficult. So I call it the era of vulnerability-dependent exploitation, which means you need to invent or discover some exploitation techniques which only applied to one specific vulnerability. And those techniques may not be very useful to apply to other vulnerabilities, but the methodology to discover those methods is very useful. So now I will talk about a case study, which is Pong2On 2014 Safari Pong. So first is a vulnerability. So as we know that in HTML, we have, in CSS, we have a concept called CSS selectors, which you can define some CSS selectors and apply those elements to some tags. So here you can see the code. I defined two CSS selectors, and in the memory it will show as 32 bytes, and each for 16 bytes. And because I created two, so it is 32. And then the CSS selector list can be mutated, which means you can use getMatched CSS rules function and to change its selector text property. So here in this example, I choose text to one CSS selectors, which means in the memory you can see that another buffer is allocated, and this time it is 16 byte, because it has only one element. However, when some function is called, the value of selector index is still 1. So 1 means the second CSS selector element, which means because now you only have one CSS selector element, but the index is 1, which means you may achieve the out-of-boundary access. Yeah, so in the function CSS selector specificity, you can see that the selector index is pointed to the memory which does not belong to the CSS selector. However, if you read the name of the function, you may think that the function only has OOB read, not OOB write, but maybe we are not correct. So a deep look of the CSS selector structure indicates that this element contains two 8-byte pointer. One is a big 21-bit value, which is aligned to 8 bytes and followed by a 8-byte pointer. So if we check the code flow carefully, we can see that in some cases, OOB write can be achieved, but it is very restrictive. It has to pass a lot of checks to achieve 1-bit write. So you can see that this is a 21-bit value, and you have to meet all those conditions. For example, the third to the fifth bit must be 11 or 00 or something like that. And all these conditions is achieved, then that value can be, the eighth bit can be changed from 0 to 1. That's a vulnerability. So what we can do, we can possibly choose some options. First, you can choose a value of 0x40 to 0xc0. This seems to be good, although we have some other possible options. They are not that useful. And also there are some other restrictions. For example, for that value, the offset 8 must be either 0 or a valid pointer. But since you currently it is on the 64-bit, heap spraying is very difficult. So you cannot put a very valid pointer just after that bit value, which is difficult. So where we are is that we have a very restrictive 1-bit write achieved. So now we should consider what to overwrite. So the first option, the first candidate is of course the WTF string implement. So we can see that it contains the some fields like the mref count. So you can maybe change the ref count from 0x40 to 0xc0, which is not quite useful, because if you can change that value to a smaller value, then the object can be freed earlier, which is good. But if you make it a larger number, it is not useful. And also, you can choose to make the mlength bigger, which is good. However, the mlength is on its higher 4-byte position, so it is not possible in this case. So the next candidate should be the WTF array buffer. So look at its structure. So it is mref count followed by mdata, which is real buffer pointer pointing to the buffer, and the next is the size of the buffer, and the last one is the m first view, which the array buffer view is assigned. That value will be assigned. Otherwise, it is 0, which is quite good. So we can see when no array buffer view is assigned, the memory layout is like this. So under the fourth field is 0 because no array buffer view is assigned. However, if the array buffer view is assigned, then the first view pointer should be a valid pointer. So let me re-emphasize the overall exploitation strategy. So first, of course, we need to achieve 1-bit over OOB write, and then we can achieve, because we changed the size from 14 to C0, so we can achieve additional 0x80 byte write, which is quite good. And then we try to achieve the AAR and the AAW. And finally, we can achieve the remote code execution. So we construct this kind of memory layout. So it contains 2 chunks. One is the 0x20 chunk, which you have array buffer right in front behind the in front of the CSS selector array, which you can use it to achieve the OOB right. And then you have a lot of 0x40 chunk, which you stored some array buffer, the real buffer, and following by a web core object, which has a vtable, so that you can leak that vtable out to defeat the ASLR. However, something we forgot, if you do this memory layout immediately, you can see that the process is crashed. This is because just after that 1-bit write, there is a loop. That loop will traverse against the whole CSS list until it finds it is the last CSS list, CSS selector list. So you can see that it used a bit which is called the is last in tag history, which is its 18th bit. If this bit is set to 1, then it means the last CSS selector is accessed, so it will quit the loop. Otherwise, it will keeping to traverse until the process is crashed. So let's adjust the memory layout. We can put another array buffer which has size 0x20,000 behind that 0x40 array buffer, which indicates that M is last in tag history is set, so that the process will not crash. If we set, we will, of course, cause some byproduct. It will have additional 20,000 chunk, a lot of those buffers. And of course, those buffers will not be wasted just for to avoid the process crash. We can use those big buffers to store the ROP gadget later on. So the problem here is that which 0x40 web core object to choose, because this web core object will be used to leak the vtable. So of course, you also need to leak the another base called the text base. So you need to have some candidate. So a typical case is that you need to have that object containing a vtable as well as a vector element, so that you can put a pointer to that vector to read some to achieve the AAR. So the good candidate, for example, is HTML link element, the SVG text element, and the source buffer list, etc. But none of them is 0x40, so that's not a good option. So we have an option 2 that we can maybe put that to the two phases. One is to put an object just having a vtable object into that memory, and then try to free it. And after we free it, we can put another object containing meeting our needs. For example, we can put an array buffer view into that memory, so that we can achieve AAR and AAW. So I will introduce the JS controlled free. So in some objects of WebKit, we can see that the object can be allocated if you set the property of that JS object. And you can free it by just unset that value. So a typical example is web core number input type. So you can see that if we set its type to number, it will allocate 0x40 byte memory. And if we make it null, it will be freed. So I call this kind of object JS controlled free. And in the WebKit, you can find a lot of such objects by searching the patterns, which is quite good. So let's adjust the memory layout. So in the 0x20 chunk, we just put it as usual. And also in the 0x40 chunk, we put that number input type in front of the overflowed buffer. So, and then we just free it. After we free it, we fill it with array buffer view so that we can achieve the AAR and the AAW. So after with those techniques equipped, we can just make the AAR and the AAW. And here is the code primitive. So the next topic is how we try to avoid that heap spraying because of the 64-bit platform. So with the AAR and the AAW, this can be really, really easy. We can just put a vtable as the base address, and then we can achieve AAR to read the content of the vtable. So after reading the content of vtable, we can leak the text section base so that we can construct the ROP. And then we can, with the AAR, we can know the address of that 0x20,000 buffer so that we can put our shellcode into that buffer and change a vtable to that buffer so that we can achieve the arbitrary code execution without heap spray. And another problem here is that how we can avoid that ROPs, because ROPs is not very stable. It relies on version a lot. So let's look at the mechanism of the WebKit on 64-bit. So you can see that upon the process creation, 128 megabyte JIT page will be allocated. And you can see that you can find the address here is quite different from other addresses like the image address or the heap address. The address is quite different. So if there is any way for us to search the memory to find that JIT page by some smart methods so that we can avoid the ROP. Actually, you can see in JavaScript core module, there is a symbol called the start of fixed executable memory pool, which will point to that JIT page, which is quite good. And you now have the solution, which is you can point just use the offset because on some specific WebKit version, that offset will be fixed, which is very good. For example, in this case, you can just use the offset 3D3B8, which is the offset of the points to the start of the JIT pool. But this is a very dirty solution, and on different version of WebKit, that offset will be different. So we can find a more smarter way to find the JIT page by looking at the source code when the JIT page is allocated. So we can find it has it just allocated a very random value and do some shift. So you can see the highest some bits are always 0, and the lower, the least 20 bits are always 0. And it has a minimum value and the maximum value. And the red part here can be even value, which can be only be 0.2468 ACE, which means it can be divided by 2. So with that pattern, we can do a JavaScript search to search that memory so that finally we can find that JIT page without any problem. So after that, we can get the code execution. So let me summarize the WebKit exploit. So this kind of vulnerabilities can impact on all WebKit apps, so it is very dangerous. However, you may need to have different exploitation techniques on different platforms. That means you have to be very familiar with WebKit source code as well as the exploitation method. So after we have this case study, we should find out find out the reason why it can be exploited, so that we can give the suggestions to the vendor. So the first suggestion to Apple is that you can put a lot of frequently used objects to heap arena. Just like Chrome, I think, for example, the typed array will be put at a V8 heap, but in Safari it is not. So maybe we can do that. And also we need to enable the memory allocation randomization. So especially for some small memory allocation, because currently the WebKit and JSC use tcmalloc, which is not quite random. If you allocate the memory for the specific size, then the memory will be consecutive. And also here, because I introduced the JS control free, those object is quite good, but it may be a tool for the exploiter to craft the memory layout to achieve the heap function, which is really bad. So maybe we can reduce the number of objects with the JS control free feature. And also we, of course, need to make the JIT page harder to guess, especially for the 64-bit. So the suggestion to Apple and Google, because they both maintain the code of the WebKit. So always I can see some security fix applied to some code branch, but it will not be applied to all the code branch, which will leave some time window for the hackers to exploit. And of course, to some OS, OEM, and some app vendors, my suggestion is that you need to upgrade the WebKit version and the WebKit libraries frequently to avoid some undays being exploited by some APT guys for a long time, which is really, really bad. So although we can still exploit WebKit, I have to admit that it is the best and the most secure rendering engine in the world. So with my research, I need to thank the following persons who helped me a lot during my research. Thanks a lot. And here, that's all for my topic. Any questions?